All right, good morning, everyone. So today I'll be talking about implementing precision frequency measurement, or PFM, using PLL. My name is Kit. I'm a hardware applications engineer with Skyworks. And this presentation was put together with the help of Greg Richmond, Nate Shashoua, and also David Spencer, who's not on this slide, important contributors. So this is what I'm going to talk about. First, I'm going to motivate and kind of explain what PFM is, why we want to do it, why we want to use it. And then what I think is more fun is how to implement such a system in hardware, because I'm a hardware engineer. Right? So I'll have a first implementation as proposed by Meta, and then another maybe slightly better implementation that fixes some limitations of PFM as proposed. And I'll have a lot of measurements and such that I'll show you. Okay. So what is PFM, precision frequency measurement? The idea is that we want to measure and then transfer the frequency from one NIC card to n other NIC cards. And we want to do it without routing a physical clock, because once we'd have physical clocks, then your compatibility with various servers and whatever hardware breaks. So the idea is to run some sort of loop in software where you put the hardware on the NIC card, so whatever time device you want, and then we have everything synchronized together over some servo loops. One side note is I think the terminology PFM is slightly, unfortunately, mistermed. I would have liked to call it more like frequency transfer over PCIe, as opposed to just purely measurement. But unfortunately, FTP has already been taken. So we'll just stick with PFM for now, and we'll call it PFM. So why PFM? Synchronization can be improved between PCIe endpoints in a commercial server. We want PTP, which is the time synchronization between like a grandmaster, like your golden clock, right? It's like the brightest star in the sky, the sun. And one of the NIC cards to be accurate. And then from what I call NIC A down to the other cards, we have this other loop that's running, multiple loops actually, PTM, and also what is now PFM. So we want to have frequency stabilization, which reduces dynamic time error, use cases like 5G vRAN, AI. And the main point, again, is no hardware changes. We just want to run everything in software. And we can reduce some of the requirements on a local oscillator. OK, so how does this work on a system level? Well, first, what you need is a clock device of some sort. In this case, Skyworks makes some devices we term NetSync, network synchronizers, and it has a couple of features on the next slide I'll go through. But essentially, you can adjust the frequency of NIC B to match the frequency of NIC A if you know what the frequency difference is between the two cards. To know the frequency difference between two cards, you can measure each local oscillator, TCXO, against a common clock. And in this case, it's the PCIe clock, 100 megahertz, coming from your CPU, server, whatever it may be. Once you have a difference in frequency, you can go ahead and subtract those, and then drive the frequency in NIC B to match whatever NIC A is going to be. And because it's in software, you can extend this to like n number of NICs, 100, however many you want, because it's just a software server loop. There's no other like hardware stuff going on. So some key features we need to make this work. We need an ability for a PLL to lock to TCXO or OCXO on the input for stability. It'd be nice to have PCI compliant output clocks, spread spectrum, and the idea is to improve the jitter, so we can't be adding jitter. So we need low jitter outputs from this clock device. We need the ability to measure frequency and or phase down to some really good resolution to be able to manage the time errors that we're trying to correct for. And lastly, we need some mechanism to control the frequency of the PLL output. And we'll see in the next slide why that is. So here's like a second level down, deeper level system diagram of what we've got. In this case, my test setups are using the IT26 as an Intel Ethernet chipset. And it's got a GPIO that'll give you 1 hertz. The 1 hertz is saying, this is what I think is my current time. And so if I can get those 1 hertz output to be aligned, then I know I've done my job. And also, on the NIC card, you would want your PLL device, your local oscillator. And in yellow, you can see that I have a servo loop running on this desktop CPU that's doing the frequency comparisons and adjustments and so forth. It'd be good to mention that I did not get this working with PTM due to hardware stuff, but as of like 2 or 3 days ago, I think I just got something that started to work. So definitely like work in progress, and we can try to do better next year or whatever. So some baseline measurements. At the top is me running PTB4L, which synchronizes the phase between the grandmaster and your NIC-A. And we see something like on the GPIO of the Intel Ethernet chip, we've got like 20 nanoseconds of like stuff going on. And we're only concerned about the dynamic timer, the constant time error, which, cables, whatnot. I'm just kind of like ignore that for now. And then on the NIC-B, we can use Linux util PHC assist to kind of get the phase to go to NIC-B. So you can see the phase is kind of like there, right? The line is flat, but you get a bunch of this variation. So what we're trying to do is reduce that variation from what it is like 10x here to something better. So in order to get this whole system to work, you have to make some hardware mods. So this is the i226 NIC card. I bought, I think it was like 70 bucks or something off Newegg. There are 2 critical things you got to do. One is you have to replace the local oscillator, which is like a crystal, with something that I can control. Because if I'm adjusting a time, I've got to be able to control it. Second thing is you need your PPS output, which is what the red wire is. And then if you also want like a PCIe clock to do the measurement, you can do that. But in this case, I had to do like buffers and balance and stuff. So I just plugged a free running crystal as the common reference, and that's also fine. The middle picture is just my desktop setup. It's my lab computer. You can see a 9-pin connector, maybe like 10 years old, who knows. So no PTM, sorry. And then on the right-hand side, you see my eval boards and like TCXOs counters and stuff like that. OK, so what is the problem we're trying to solve, right? We're trying to synchronize the frequency from NIC-A to NIC-B. And by extension, if you synchronize the frequency well, then your phase is also going to follow, and it's going to not be as jittery. What contributes to the phase jitter is a combination of your local oscillator that's just running, right? So if your i226 is referenced to a crystal, your output GPIO is going to be no better than the crystal. Maybe your phase is good, but then your jitter there is going to be no better than that. But also, your noise is coming from whatever the Ethernet chipset decides to add as noise. And unfortunately, there's a whole bunch of noise that it's trying to add. Because the Ethernet chipset itself cannot adjust its own reference clock. Well, it can, but you see in the second, that the middle column is where it attempts to correct its own frequency. So with PTB4L running, you can see that with NIC-A, we start at some nominal frequency. We don't care what it is. And then it tries to correct it by putting these like cycloslips or something like that. So now you get these frequency spikes. But by the way, the graphs there are frequency on the vertical and time on the horizontal. So when you see these vertical spikes, these are frequency excursions from what it's supposed to be. And whenever you get frequency excursions, now you get this like phase garbage that comes out, right? So we don't want that. We don't try to fix that. NIC-B, while it's unsynchronized, is at some random other frequency. We don't care what it is. We just need to know that that needs to be fixed. And then when you run PHC assist, now, OK, it's saying the grandmaster in this case is somewhere in between A and B. So like A is pointing down, B is pointing up, right? We want to get rid of that. So because I now have the ability to control the system clock, the system of the i226, I can just move the frequency, and that gets rid of all your spikes, which means that fundamentally your noise is no longer there. And so if you fix the stuff in the frequency, you fix the stuff in the phase. So here's the graph in the phase domain. Same kind of graphs as before, but it's like a different run, so maybe a little bit different. So NIC-A, when you have a phase slope like going down, that means your frequency is not aligned to whatever your grandmaster is. Same with NIC-B. So A and B are different frequencies right now. If you look at the kind of phase variation, after you run PTB4L or PHC assist, there's like some variation. And then after you enable PFM, the servo loop, you can see that reduces something like 3 or 4x, and it looks much more like regular. And the problem with this system is that I figured this out 2 days ago, but my grandmaster was doing like this test box called like Ether10 Genius. There was some setting that wasn't right, and I replaced it with like a Calnex Paragon X, and it seems to have like fixed a lot of these problems. So maybe for next year, we'll actually make the PCIe card and make some measurements, something like that, and hopefully do a little better. So there's some fundamental limitations with the first method in that we are measuring with respect to a common reference clock. And this common reference clock is just some like free running crystal. And if you run this PCIe clock can also have spread spectrum, et cetera, so it's really, really noisy. And when you sample NIC A and B asynchronously, there's also this sampling time error that you get that you can't get rid of because you never quite know, okay, am I going to sample this at the exact same time so that I can correct the frequency on the other card based on those measurements. So if we can get rid of the CPU clock altogether, then we just get rid of that problem. So that's the proposal here is the 98 came up with, which essentially takes all the stuff, all the servo stuff, and it brings it into hardware. And the hardware only runs on the NIC card, so there's essentially zero software involved. Like your server doesn't care. Just so your PCIe card exists on your server, you're good. You have this kind of time alignment and frequency stabilization going on. So how this works is you have to be careful about what frequency and phase mean. Every signal has a frequency, but that signal also has a phase, right? They're kind of like different concepts, but they're also like part of the same thing. So if we know the phase out of NIC A, we can correct the frequency that we're putting into the I226 by just running a hardware PPS loop on the NIC card. So this is not wiring across PCIe bus. This is locally, just like one trace on the PCB board, right? So once we have the I226 sorted out, it's stable. So now PHC assist can route that phase all the way to the NIC B, CD, et cetera. And in this case, you need to run it, you got to pick your bandwidths wisely, et cetera, your sampling rates. But in this case, you can actually kind of filter out your frequency and your phase jitter by getting just the average and driving the average frequency back into I226. And now you've got everything you're synchronized. You need to be a little bit smart about how you enable and disable various things. But you can see that here I get another maybe like 2x improvement over what the previous method is. And that's, the previous method, I wasn't even running like temperature or lows or whatever. So this is a idea for consideration. So call to action is, would it be really nice is I think next step for me is to make this PCIe card. And then it would be great to have partners who actually have servers that we can plug the cards in and like make some measurements. Or even like before then, during development, have somebody to help and guide us along the way and kind of do some exchanges. So great. Thank you.